I think it's vertex. To singular of the vertices is vertex. Okay. So you start with C.
Ondan sonra connected olanların en küçük cost olanını seçiyoruz.
So the Prim's algorithm starts with the arbitrary choice. So you could have started with any vertex. I saw some of you start with G, probably some of you start with A. It's just a random choice for the first vertex.
CG'yi seçebilirdik.
İngilizce yazdık.
So we could choose this one instead of this.
Okay.
That doesn't matter.
So sometimes you have two choices, and you can choose the one among the ones say same cost. You can choose the one you like. You can have more than one choice, and that's okay. I actually sent you an Wikipedia page which had the Prim's algorithm in there. One of the last references on that web page was a YouTube video, if you could watch it, which shows how a typical Prim's algorithm run. There are so many videos how these algorithms run. You could find, I think there is connection to YouTube from Beacon, so when you're inside Beacon, you can check some of these out. You could make a running video of this, like how each vertices are chosen and continuous time video to see how this is done. So starting with C, choice was A, the next vertex. So now you have A and C. Among the ones that connects the A of C, there's A, B, C, D, or CG. And then now we're making the choice of the lowest cost one, which was that.
Do we have to write the other ones, or just this is a loop because it's an iterative process?
You can just say, so the next choice for the next one, the pairs you're looking for are AB, CD, and GF. So the candidate Y's are B, D, and F. Remember, you mark these as actually X. So the procedure starts with some x0, and then you choose y0 according to the cost to connecting to x0. The minimum cost vertex is called y0. And in this case, the y0 is A or G. You choose one of them, and then that y0 is chosen as x1. So in this case, A is chosen. So this is your x1. Once x0 and x1 are chosen, you're looking at all the vertices that attach to A or C. Among the ones attached to A, B is the one lowest cost. So this is your y1. And among these ones, this is the lowest cost one. So this is your y0. And among the y's, you choose the one which has the lowest cost. In this case, this becomes the lowest cost. So this becomes your x2. Once you choose x2, x1, and x2, then you're looking at possible ways to connect this to the rest of the graph. So this becomes your x1, this becomes your y0, y1, and this becomes your y2.
After choosing these vertices, now we have
three possible
edges, and we choose the minimum cost, which is this one or this one. It doesn't matter, they are equal. I choose that one.
So this becomes naturally your x3.
Yes. Now, I look for the connected edges from vertices I choose, x1, x0, and x2, and x3. The possible edges are BE, BD, CD, and GF. I look for the minimum cost one. I choose that one. Doesn't matter, I could choose the BE.
So once you choose that, this you declare as X4.
Now I look for in its same process, look for the minimum cost among the connected ones. It's the 2. I could choose BE.
Okay. And then that becomes an X5.
Now I choose, again, look for the minimum cost among the vertices that I already visit. I could choose this one, but it could create a cycle here. So
no. See, with these prims, actually I was going to ask you, in the grid algorithm, you always have this line in the algorithm which says that choose the one which has lower cost, which does not create a cycle, right? But in prim's algorithm, we never had that line. So why don't we ever have to check for if something causes a cycle or not?
Because we are forming a tree, and we are not looking for a vertex which is already in tree.
See, for each of these x, we're choosing a y as a candidate, but those y's are always among the rest of the graph. So we never look at the already chosen xi's as possible y. So for x2, for example, when we're choosing y2, we're looking at this one. But for x4, when we're choosing y4, we are looking at this one again. We are not looking at other vertices. So for example, for x5, when I am looking for y5, I do not look at this because this is already chosen as x. So because of that, I cannot have really a cycle by my choice of y's, because y's are always chosen outside of already chosen graph. So this already chosen sub-tree, the vertices of that are not candidates for y's. So they are not candidates for next choice of x as well. So you can never choose this edge because this vertex is already taken, okay? So for this one, the candidate y5 is only this. It's not B. The candidate is only F, okay? Because of that, you can't create a cycle. Okay, so then you choose.
Candidate is F, but I could connect it from G or E, but the minimum cost is connecting, comes from connecting from D. So I connected this one.
It's called an X6. And then it finishes the algorithm once you choose all the vertices. And it's automatically connected. There's actually a proof for prim's algorithm for connectedness. And the fact that it doesn't have any cycles, it's a tree. So you can... The one in the video, actually on YouTube video, it was slightly differently stated. The algorithm can be stated in different ways. The video stated it like you actually say you start with C in this case, and then you do A. Let me graph this first. Some of you may find this running easier to understand. So you start with some vertex, call this x0. The algorithm starts, say, with C, okay? Now with C, think this as a point that all the neighbors are this. So you look at this, your graph is just C now, subgraph, and your neighbors are this. Among the neighbors, all the lines highlights. And then from these lines, you choose one of them, say A, and then you choose this line. Once you choose that line, your subgraph is that. Okay? So now this becomes x1, and this line is your subgraph. With that light, with that part is your subgraph. Your neighbors are these now. And among the neighbors, you look at the edges that connects your subgraph to the neighbors. So you have 3, 9, 7. You don't look at anything else. So among these 3, 9, 7, 3 is the cheapest one. So it's the same algorithm, but stated in a slightly different way. So once you choose that 3, now this is your subgraph. Your neighbors are these. So it's like the, one of these computer games. Suppose that you have a country, you're occupying the neighbor countries by one buying, attacking them. There's computer games who does this. So you're here, you look at all possible ways you can attack the neighbor countries. This is this, this is this, this is this. You look at the cheapest way to gain a new country. So among them, these 7s are the cheapest way. You choose one of the countries and attack them, and you occupy them, you get them. So once you get these countries, you look at the thing. Of course, you don't attack your own country, right? So it's already yours. So you look at the other places that you can attack. So from B, you can attack to D or E. From G, you can attack to F. So you look at all possible costs, attacking from your own country to something that you haven't occupied yet. And then you find that this is the cheapest one, or this one. So you choose one of them, you occupy. It's always your countries and the countries you haven't occupied yet. So from these, you look at all the neighbors. In this case, neighbor graph is everything. So you look at possibilities, and these, and these, and then you occupy one of the countries according to, again, being cheap. And then you finish it by occupying here. So again, from D to E, you don't attack because you have D and you have E as a part of your country. So you don't consider attacking to your own country. So you have to attack to neighbor country, which is not there already. So you can run your algorithm like this to thinking you're occupying countries. Now, in that Wikipedia page, there was also discussion of how, like, it's slightly cheaper to calculate distances. So once you, once you choose certain vertices, you're not calculating this again. Okay. So suppose that we went to here. How's that? Yeah, I mean,
We are calculating it again and again, but at some point we don't need it because we have the vertices in the tree, which is a neighborhood by 9.
Is there a graph where you can show one edge is never calculated? I couldn't tell. It seems like you always have to calculate it beforehand. So I'm not sure it's anyway. Okay, so this was the quiz problem, and hopefully I saw many of you did it, so it should be all right. We have an exam coming. Midterm 2 is coming, not this coming Tuesday, but the Tuesday afterwards. So it's April 29. I should say that. This was announced at the beginning of the year. So I should say. It's going to be during class hour again. So not this Tuesday, the coming Tuesday. Because it's Tuesday class, it will start at 3:30, 3:40, rather than 1:40 last time. We again have 2 classes, and go to the same room you went for the midterm 1. Okay, so we have 2 classes, which is here and I will make these announcements more next time. I think this is 05, and then we have 03 as well. Huh? So you were here, and then you will come to here. Ah, not SAS, Beyze. Yeah. So some of you were in the other room across. So I mean, both of the rooms are large enough, but if we equally divide it, it will be good. So I am thinking that today we will do cliques and independent sets, and then Euler circuits. Next week I will do planar graphs on Tuesday class and Friday class. And some of the Friday class we can solve questions, how like typical problem comes in the graph theory, and then you'll be ready for the exam for the Tuesday afterwards. Tuesday mornings I don't have an official, I mean the official office are on Thursday. But if you think it's too far away, many of you said it's too far a couple of days ago. I can also do extra office hour on Tuesday morning. Okay, so use on office hours if you need to use. There will be at least 2 questions that have 1-page detailed proof writing. Out of 5 questions, 2 of them probably will be writing a detailed proof. So if you are not comfortable with writing such proofs, you should read all the proofs that I did, try to do your own proofs, and then if you can't do any of them, come to my office hour. We can talk. But other half of the exam will be standard knowledge checking and standard small steps inside these proofs. So I will give some examples of them. But like the inequalities you learned today, there will be questions that just checks if you know them.
Can you upload sample midterms or email?
Yeah, I will. Last time I was a little late with that, but over this weekend I will prepare one and send you an email. I have actually quite a question bank from previous years. So I can send you more than 20 questions from earlier exams that I had before. As I said, I mean, some of the questions will be proofs and difficult, but many of the questions will be just checking if you just read through your notes. So don't be discouraged with the fact that we have done so many proofs and so some of the things were difficult. But a lot of the exam will be just general understanding of graphs. And, next week I probably will outline a little bit more about what kind of questions. But the planar graphs also have some inequalities and some straightforward questions that you can probably do without being able to write long proofs. Okay, so one of the things we were doing last time, cliques and independent sets. I was trying to get to Turan's theorem, which I stated last time, but I didn't get a chance to explain why it's true. So recall that a clique of size k in a graph G is a subgraph is a subgraph, is a complete subgraph. It's a subgraph which is complete. Which is a complete. K vertices. So clique, by definition, is a subgraph with k vertices where any two vertex are connected by an edge. So a clique with size 3 is a triangle. A clique with size 4 is something like this. So you're looking if you can find such things inside a bigger graph that you have. So this is, for example, this 1, 2, 3, 4, 5, 6, 7, 8, 9. This is an example of a graph. And 2, 4, 5, 6 forms a clique of size 4. Forms a clique of size 4. Okay? So complete graph of size 4 inside your graph is a clique of size 4. Now we define maximum clique size. So graph G, maximum clique size of a graph G is the maximum positive integer K such that G has a clique of size K. You see that this graph has also a clique of size 3. So like 4, 8, 9 is a clique of size 4, 8, 9 is a clique of size 3. Obviously, the maximum clique size here is 4 because you don't have anything bigger than. So in this case, maximum clique size, we denote it by MC. So we denote this by MCG. So in this example, MCG is 4. Okay. So this is the setup. So the other notion is independent set. An independent set is a subset of vertex set in a graph G. G is a subset of the vertex set such that subset, say A, of vertex set such that for any ij inside the subset, this ij is not an edge. So it's a subset of your graph or vertices so that if you take two vertices in the set, you know that there is no edge between them. So they sit independently inside your set. This is your definition. So for example, I could see that here, if I take 1, 5, 4, 7, and 3, it's an independent set. In this example, 1, 3, 5, 4, 7 is an independent set. Okay? Because there is no dependency between them through an edge. Of course, there's certain relations between independent sets and connected components and so on, but we will not discuss that. So all the things we will be doing in terms of estimating the sizes of such things starts with this one result about independent sets. For independent set, we also have maximum size of an independent set. The maximum size of an independent set is denoted by. So we can choose our notation. Use the book I'm using, which is the in Grimaldi, they don't mention this much, but the Sheldon Rose book uses alpha G, alpha graph G. So we can use alpha G if you want. We can also, just to remember, we can use int of G. Because it's harder to remember alpha G, what it means. So in the exam, if I say int G, you will probably remember this easier. So this is a number, integer, that you can, for any graph, you can calculate it by checking a graph and how big the independent sets you can find. For example, here, probably 5 is the biggest one, but yeah, it's hard to find 6, I think. So out of these 3, you have to choose 1. Out of this, oh, this is not independent. You should have warned me. 4 and 5 are connected, so you can't choose either, right? You cannot do that. So you have to choose one of them. So let's not take 4. But if we do not take 4, then we can take 8. So we can still find it like this. So you can put 8 there. Okay. So independent set by rule should be formed by vertices which has no edge between them. Okay. So in this case, independent set size is 5, I think. You can't find 6. Now there's this estimation, which is this formula, or estimation. For a graph G with vertices, say 1 to n, we have the size of independent set is bigger or equal to the sum over 1 to n of 1 over 1 plus di. So if we run this for this example, sometimes it does not give you the independent set. This is not big enough, okay, to give you exactly independent set, but it gives you an estimate. It's a good way of getting an estimate. So what's di? Di is the degree, right? Where di is the degree. Is the degree of the vertex I. So in this example, d1 is 1, D2 is 3, D3 is 1, D4 is 5, D5 is 3, D6 is 1, 2, 3, 4, D7 is 1, D8 is 2, D9 is 2. So you add 1 to these, you make 1 over, you add them up, you get a lower bound for your independence number. So the sum, as I said, this could be sometimes much smaller than what you want to find. So 1 over 2, 1 over 4, 1 over 2, 6, 1 over 4, 5, 1 over 2, 3, 1 over 3. So you get 1 plus 1 more 11 over 30, 2 over 3, 10 over 30, 31 over, so it's 3.1. So it's very, so 3.1 means independent set is 4 or bigger because it's always an integer. And we already found some independent set size 5. So this fails to be a good estimate, right? Because this is 5 and you can only find that it's bigger than 4. As I said, it's a crude estimate. It's not the best. I mean, you can see that this will change with respect to the graph, so you cannot just say it's equal to that. All you can do is give lower bounds like this. But it's good to know this estimate. And you can also see why such an estimate exists, because when your degree is bigger, that means at every vertex you have quite a bit edges coming out of it. It means you have in general many edges. So when you have big edges, a lot of edges, 1 over means you have very small number here. And you're summing smaller numbers. That means your lower bound is small. Why? Because you have too many edges means independence number is small. Because everything is connected to each other. For example, in a complete graph, you can see that these are very big. So when you sum them up, your independence number just drops to 1. I can actually do that case quickly. Is it time? Okay, it's 32. So let me do this and then we give a break. Okay, so take a complete graph with n vertices. So complete means there is edge between any two vertices. Okay, so this is a complete graph with n vertices. Now, what is the degree of each vertex in this case? It's connected to everything except itself. So degree is n minus 1. Now, if you do the sum over the vertices of 1 over 1 plus di, you get the sum over 1 over n, because you add 1, of n many things, so you get 1. So your lower bound for independence number is 1, which makes sense, because in this case, your independence set number is 1. You cannot find two points which are not connected. So it's best estimate in some cases. Okay, so let's take a break, 10 minutes, and continue the next hour.